So maybe it's a good idea for us to get started. So we're gonna have Newton now, Newton Cheng from UC Berkeley. He's gonna talk to us about hypergraphs and entropy. So please, Newton.
All right. Thank you for the introduction, Hugo. I hope everybody is staying safe and healthy. So yeah, as Hugo mentioned, I am a graduate student at UC Berkeley in Raphael Busseau's group. But today I'll be talking about something that is not related to gravity. I'll be discussing these objects called hypergraphs and how they can be used to model the structure of entanglement in certain classes of states. This is work that has been done in collaboration with Ning Bao, who is a postdoc at Berkeley and faculty at Brookhaven. Sergio Hernandez Cuenca, who is a graduate student down at UC Berkeley, sorry, not UC Berkeley, UC Santa Barbara, and Vincent Su, who is another graduate student in Raphael Busseau's group. And if you want, the associated paper on the archive is, this is the tag here. Okay, so to briefly introduce what I want to talk about, I'm sure pretty much everybody watching knows that the von Neumann entropy is probably one of the most important quantities in quantum information for a variety of reasons. It captures the correlations of a quantum state. It has like really nice axiomatic and operational meanings. And for our purposes, we are interested in it because it is useful for classifying certain sets of states. So some really basic inequalities that this von Neumann entropy satisfies, you can see, are of course you have the subadditivity inequality, which you may also know as the positivity of the mutual or non-negativity of the mutual information. This inequality is strong subadditivity, and then this is the standard triangle inequality for the von Neumann entropy. So these three inequalities are known to apply to essentially all quantum states, but we could very reasonably ask, well, what about other classes, sort of more restricted sets of states? Are there certain inequalities that only apply to very specific sets of states with very specific properties? The answer, unsurprisingly, is indeed that is the case. And sort of to kind of spoil the direction that this talk will take is, and sort of continuing on with the theme of the talk so far, is we're also going to be trying to look at how we can leverage techniques that have been used to study quantum gravity, that have been used to study high energy phenomena, and apply those to study quantum information or aspects of quantum information in more generality. Okay, so kind of more generally, you might ask, why should you care about entropy inequalities at all? And just to kind of give you a really short answer, the way I like to think about it is that computing the von Neumann entropy is hard. Right? If you want to actually compute it explicitly for a state, you have to diagonalize the density matrix. And if you're working in, say, the realm of gravity, where these density matrices, even if first you have to make them finite, and then they're going to be they have these enormous dimensions. That's not really a tractable problem for us. So we want to use inequalities instead to sort of avoid computing this von Neumann entropy. We can use these inequalities to just constrain the allowed values of entropy. So some applications of this include getting insight into the structure of states and entanglement, this like monogamy of entanglement. You can kind of phrase it using inequalities. Of course, you can use them. They're extremely important for understanding information transmission and communication, for example, in proving converse theorems for certain channel capacity theorems. And of course, as my group knows very well, entropy inequalities are extremely important for understanding energy conditions in gravity. As I mentioned earlier, though, the interest in this project is we want to use these inequalities to classify sets of states. So what do I mean by that? I mean that, as I mentioned in the previous slide, for sort of full generic quantum states, those three inequalities I put previously are true for any three-party quantum state. But for more restricted sets of states, we actually can do a bit better. So for example, for this class of states that we call stabilizer states, which if you're not already familiar with them, I'll briefly introduce them later. We know the complete set of inequalities that four-party stabilizer states satisfy. And as of, I think, like relatively recently, maybe 1 or 2 years, we actually also know the complete set of entropy inequalities for holographic states for five-party holographic states. So what does this tell us? So just as a super simple kind of classic example, if, say, I handed you a GHZ4 state, you could immediately tell me that it doesn't correspond in any sense to a holographic state, to a state that is dual to some geometry, because it violates one of the inequalities that holds for holographic states. So that's what I mean when I say we want to classify these states. So before I kind of go into some more details about the project, I just want to introduce a little bit of terminology. So if I hand you some n-party state, you can compute all the marginals, all the reduced density matrices of the state, compute their von Neumann entropy, and then store that information in what we call an entropy vector, which lives in R to the 2n minus 1, which we call entropy space. So just as a, the sort of simplest non-trivial example, I have this two-party state here, rho A, B. I can compute the von Neumann entropy on A, von Neumann entropy on B, and then the entropy of the entire state AB. And I'm just going to store this in a three-dimensional vector that's living in R3. And we'll call this the entropy vector of this particular state. Okay. Now, if I am looking at some subset of states and I consider the sort of the collection of all the entropy vectors, that forms the so-called entropy cone. Now, the cones that we're going to be interested in are polyhedral cones. So these are cones that kind of match your intuition for what a geometric cone is. They're convex in the sense that they're closed under linear combinations with positive coefficients. They have finitely many facets and finitely many extreme rays. I have a picture on the next slide if the intuition's not immediately clear, but the idea is that when I hand you some inequalities, the inequalities kind of carve out facets in this entropy space. And then you can think of these extreme rays as kind of being the intersections of these various inequalities. And these provide two ways to kind of classify or completely describe these cones. So in this picture that I stole from the original holographic entropy cone paper, you can see this is kind of the simplest non-trivial entropy cone, the two-party entropy cone. You can see this is just 3D space with these three axes corresponding to the different entropy directions. And you can see that by applying subadditivity, which is this one up here, and then the triangle inequality gives you these two over here, you get this kind of triangular cone that is carved out of this R3 space, and every sort of allowed quantum state corresponds to an entropy vector that lives somewhere inside this cone. And you can see it consists of these three facets, this one, this one, this one. But alternatively, we can also equivalently well describe this cone by the intersections of these various facets, these three rays over here, and these are what we call the extreme rays of the cone, and they kind of form this like basis for which we can build any entropy vector inside this cone. Okay. Okay, so now let's pivot back to some physics. I just want to reiterate that computing the von Neumann entropy in general is hard, and we don't want to do that, particularly if, say, we're interested in gravity. Now, fortunately, we have an easy way out if we're working in the realm of ADS-CFT. We know that, at least to leading order, the von Neumann entropy is given by this RT formula, the Ryu-Takeyanagi prescription. I'm sure most of you are familiar with formula, but basically all this formula says is that if I am looking at some region A of the boundary CFT, its von Neumann entropy at leading order is given by the area of this surface, of some surface, and multiplied by this constant, where the surface is the one of minimal area, which is homologous to the boundary region and has the same boundary as this choice of region. I'm sure, again, many of you know this formula. But the reason this formula is so important is because it sort of geometrizes the problem of computing the von Neumann entropy, so that instead of diagonalizing this enormous matrix and then taking the logarithm of it, instead all I need to do is compute the areas of some geodesics in some given metric. And in particular, this is very useful because if we're only interested in entropy inequalities or classifying entropies, I never need to actually do the calculations themselves. Instead, I can just sort of think about the problem geometrically. I can skip the calculation and just start to think about how the geometries of these surfaces combine. And this is essentially the technique used in this paper from 2011 from Patrick Hayden, Matt Hedrick, and Alex Maloney, where they proved that this quantity called the tripartite information, which is just some linear combination of von Neumann entropies, has a definite sign. They never need to actually compute what these entropies are. They just show by these kind of cutting and pasting these surfaces that the sum of areas of some set of these surfaces is greater than or equal to the sum of areas of some other set of surfaces. So they never need to compute the entropies. They can just make arguments based on the geometry of the problem. However, as you might imagine, if I'm cutting and pasting surfaces that correspond to these different regions, this quickly becomes difficult to handle once I start getting to larger party numbers. So just reference this. This is a three-party or four-party inequality, depending on how you want to look at it. But once you get to 5, 6, 7 parties, these cut-paste arguments start to become very cumbersome to handle. You saw that like the entropy space scales exponentially in the party number. So once we get to even like double-digit party numbers, this is pretty much not tractable. However, there was an insight that came when thinking about this RT formula, and this insight was to treat this minimization in the RT formula not just as this minimization over this area, but to treat this minimization as kind of an honest min cut in graph theory. And this is not a original observation in the sense that this notion has appeared before. So for example, in the tensor network story of holography, where my RT surface is this cut that's cutting some like tensor legs, you can think of this as kind of a min cut over a special kind of graph. In the bit thread story, they are essentially using the dual formulation of min cuts as flows on a network. And so this insight has appeared in various forms in the field, but it's very useful in terms of entropy inequalities because it sort of, again, changes the way that we think about the problem of determining entropy inequalities in a way that I'll specify more carefully in a second. But again, let me just take another quick detour so I can be really clear about what I mean when I'm talking about honest min cuts in graph theory. So when I hand you a graph, what I'm really doing is I'm just handing you a collection of vertices and edges that connect those vertices. To each edge, I'm going to associate some non-negative number, which I'm going to call an edge weight. And a cut is exactly what it sounds like. A cut just kind of partitions the vertices into disjoint sets. Now, what I want to do is I want to fix a set of vertices that must be separated by the cut, and this is essentially equivalent to kind of choosing the boundary region in ADS-CFT. And then I'm going to minimize over the sum of the edge weights that this cut will cross in partitioning these vertices. So in this super simple example, you can see that what I want to do is I want to separate this A vertex from B, C, and O. And so I want to minimize over all cuts that do so. And you can see that in this first case, kind of the cheapest way to separate A from everything else is to just cut this one leg here, and this has weight 1. On the other hand, on this right-hand side, the weight of this leg is now 3, and so it's now cheaper, in fact, to cut these 2 legs, which will give a sum of 2, to separate A from B, C, and O. So this is how the dynamics of the min cut comes into play. Okay. excuse me. And then we'll just simply call the sum of the weights that the min cut passes through, we'll call that the discrete entropy or just the entropy of the min cut. So now that I have this definition of entropy, how can I leverage this to start thinking about entropy inequalities? Well, suppose I hand you a candidate entropy inequality of this form. So this inequality is just organized so that these alphas and betas are always positive. So, I move all my negative terms over to this side, and generically I will write my inequality like so. Now, in the holographic entropy cone paper from 2015, they showed that there is a very nice algorithmic method for proving inequalities about these graph entropies called the contraction map proof method. Now, I won't get into all the details, but the gist of it is that I will assign two vectors of bits, so vectors of zeros and ones, to each party that appears in the state, corresponding to whether the party appears on the left-hand side or the right-hand side. And then you can show that inequality of this form, an inequality is valid if there exists a map F that brings the left-hand side vectors to the right-hand side vectors that contracts. And so what that means is that if I take the coefficients that show up in the entropy inequality up here, and now I put them into a formula that looks like this. So these x's are these vectors of bits that I was referring to. If this inequality is obeyed, that is, F is a contraction under this inequality, then the inequality is true for the graph. So then the problem then has reduced to, as I mentioned, an algorithmic one. It just becomes a question of, when I hand you a candidate entropy inequality, can you find a map F that has this particular contraction behavior? And in the holographic entropy cone paper, they provide like an example of a greedy algorithm that will do this for some candidate inequality. But the point being is that there is a kind of well-defined, even if it's not necessarily efficient, there's a well-defined way of proving inequalities on these graphs. So just as an example, here is the contraction map for strong subadditivity. We have this vector of bits corresponding to these parties, A, B, C, and O. We assign them a 1 or 0, depending on if this party appears in this region. So this is the left-hand side of strong subadditivity. This is the right-hand side of strong subadditivity. And then you can sort of easily check visually that this bitwise distance, the number of bits in which they differ from any pair of vectors on this left-hand side, is not less than the corresponding distance on the right-hand side. This is like a super simple example, but you can just kind of see the principle of how it works, assigning vectors of bits to this side and then assigning vectors of bits to this side. Excuse me. Okay, so where this stands is that now we have a method to prove entropy inequalities about graphs, and we want to relate this to the holographic entropy cone. So using the contraction map method, one can show that graphs satisfy holographic entropy inequalities, which implies that the graph cone is contained inside the holographic cone. That is, you can think about these holographic entropies inequalities as kind of bounding inequalities for the graph cone. And then we know that we know what the holographic extreme rays are. We know what the extreme rays are for the holographic entropy cone, and the holographic entropy cone paper provides a method for sort of how to convert these geometries into graphs. And that is to say that every holographic extreme ray is representable by a graph, which has the corresponding entropy vector, which then implies that the holographic entropy cone is contained inside the graph cone, or more precisely, that the holographic entropy inequalities are tight for graphs. And therefore, we have these containments in each direction. These cones precisely coincide. And here's just a picture that I really like, showing how this process works. This is one of the extreme rays of the holographic entropy cone. That is, this is a geometry corresponding to an entropy vector, which is an extreme ray for the holographic entropy cone. And the idea is that when I hand you some geometry, you can sort of shrink it down into a skeleton of a graph, like so, this sort of this shaded bit. And then the process also works the other way. If I hand you some graph, you can kind of fatten it up to become, have this kind of wormhole geometry. Okay. All right. So I spent a lot of time talking about this past work about the holographic entropy cone to really emphasize the link with our current work, which is not holographic or related to gravity. In particular, our work is essentially a generalization of that technique, of that strategy of using graph theoretic concepts to prove these holographic entropy inequalities. What we wanted to do is we wanted to take the strategy and see if we could make more statements about more general classes of states, not just holographic states. So by taking these graph entropies as kind of honest quantum state entropies, a natural generalization is to, instead of thinking about graphs, we think about hypergraphs. So a hypergraph is just a generalization where instead of regular edges, which connect two vertices, I want to now think about hyperedges, which can connect more than one vertex, yeah. We call an edge that contains k many vertices a k-edge. And you can see a couple examples here. So for example, this is a 3-edge. It is an edge that contains 3 vertices. This is a 4-edge. This is an edge that contains 4 vertices. You can think of it as just a bag that kind of contains vertices. So why are we motivated to think about this generalization? It's because the GHZ states have a very natural representation in terms of these hypergraphs. So what do we know about the entropies of GHZ states? We know that they're completely symmetric for any bipartition of the system. And we know that tracing out any part of the subsystem destroys entanglement in the sense that it leaves you with a separable state. And it turns out that a hyperedge has all of these properties. So if any bipartition of this state or this state will remove this hyperedge, which sort of manifestly will give me the same value for that cut, and sort of kind of by removing this hyperedge, I'm kind of destroying the entanglement between these vertices if I want to interpret entanglement as being due to these edges. So this is kind of just a heuristic, but it seems very naturally motivated from the kind of perspective of what the edges represent with respect to entanglement. So if I take this correspondence seriously, this hypergraph entropy cone should be strictly larger than the holographic one, because as you can easily calculate, and as I mentioned at the very beginning of the talk, this GHZ4 state violates that tripartite information inequality that is true for holographic states. So just to reiterate, if I am taking this holographic entropy, this sort of hypergraph entropy cone at face value as being valid, then we have immediately found a much larger entropy cone. And this is precisely what we found when we started working out all the technical details. So here's just I list some technical results that we found, and I'll talk about like their sort of fun physical interpretations in a second. But all you really need to know is that if I hand you a hypergraph, min cuts are still well defined. So we can still define a discrete entropy in the same way as the sum of the weights of the hyperedges that you've cut. This generalization of that contraction condition I mentioned before still holds. It sort of, instead of being a single condition, it becomes like a sequence of conditions. And there's this generalized notion of what it means for a graph to contract. We have these, and I don't want to mention the details because it's just some technical aspects about how we handle these like vectors of bits that we've assigned to every party, but suffice it to say we have some nice generalization of this contraction condition that will continues to hold for hypergraphs. We have a pleasant result that allows us to tightly bound how the number of contraction conditions we have to consider. In particular, if I hand you some candidate entropy inequality, any inequality that contracts on a hypergraph with rank that does not, up to the number of terms that appears on the right-hand side of the entropy inequality will be true for all hypergraphs. So this is particularly important, for example, for subadditivity, which is, as we all know, probably the simplest entropy inequality there is. We would like to not have to prove that inequality for all hypergraphs of arbitrary rank. And fortunately, by this result that we proved, you don't need to do that. You just need to prove it that it's valid on a very small hypergraph, and then it'll be true for all hypergraphs. Okay, so in summation, we have this collection of technical results that allows us to think about the entropy of hypergraphs corresponding to min cuts on these hypergraphs. That's all I really want to say about it. Obviously, I'm happy to talk about it in more detail after the talk. But physically, this may be what we're all more interested in. What does this entropy cone represent? Spoiler, I'm going to be talking about some class of states called stabilizer states. And as you might guess, these are going to be the states that correspond to this entropy cone. So there's this set of states that are very important in quantum information and quantum error correction called stabilizer states. And I think actually Charles mentioned them in the very first talk today as well. We call them stabilizer states because these are states that are defined as the unique state vector that's stabilized or has eigenvalue 1 from some given set of Pauli operators. Equivalently, from a circuit perspective, you can think of them as the set of states that are obtainable by applying some limited set of quantum gates. And as I mentioned, they're important for a variety of reasons. They're very important for error correction and near-term quantum computing. They have very well understood entanglement structure, at least at the low party level. And for our purposes, the 4-party entropy cone of stabilizer states is known. In particular, if you include those 3 entropy inequalities that were true for all quantum states that I mentioned at the very beginning, and we append to it this inequality called the Ingleton inequality, that completely defines the 4-party stabilizer entropy cone. Now, for the fun results from our work, we were able to show that the tripartite information does not hold for hypergraphs that include 4 edges. Now, this is good because recall that I mentioned that the GHZ4 state manifestly violates this tripartite information, this monogamy of mutual information. And we were trying to argue that 4 edges in the hypergraph language corresponds precisely to a GHZ4 state, or at least GHZ4 type entanglement. And so it's good that at the 4-graph level, where I start to see this GHZ4 type entanglement, that this monogamy of mutual information no longer holds, because we know that that should already be true. Moreover, we were able to do something even stronger. We were able to show that all the extreme rays in the 4-party stabilizer cone are representable by hypergraphs. So there are 7 extreme rays in this 4-party stabilizer entropy cone. And here are the 7 hypergraphs that correspond to those extreme rays. So we were able to show that, and we're able to show, using this kind of generalized contraction condition, that all of these all of the inequalities that define the stabilizer entropy cone for 4 parties are satisfied for hypergraphs. That is, the hypergraph entropy cone satisfies all these entropy inequalities, and it satisfies them tightly, so it can achieve them. And what that proves, as we showed in the holographic, as was shown in the holographic entropy cone paper, is that the 4-party stabilizer entropy cone and this 4-party hypergraph entropy cone coincide precisely, that they're the exact same cone. And so here's just an example of what it means for us to have proven that the Ingleton inequality holds for hypergraphs. We were able to find this contraction map that satisfies that contraction condition. Again, I don't really want to go into all the details, but suffice to say, we have this kind of very well-defined object that we can use to show that the inequalities are valid for hypergraphs. Okay, so to briefly summarize what we did is we found the 4-party hypergraph cone. We showed that it was precisely equivalent to the 4-party stabilizer entropy cone. And actually, we found most of the 5-party hypergraph entropy cone. At the end of the day, we were, as you might imagine, we were limited by like the computational cost of finding these contraction maps are bound on kind of the, as I mentioned before, the bound on the upper limit of hypergraphs you have to consider. The rank of these hypergraphs is determined by the number of terms on the right-hand side of the entropy inequality. And the sum of these entropy inequalities we're looking at have a lot of terms, and so computationally it becomes extremely expensive. But we have found, we're able to find most of it. From a kind of more abstract level, we were able to generalize tools from holography to more general quantum systems, which is very exciting because the relationship usually goes the other way. So it's very nice that we were able to take something from holography and use it for more general quantum information purposes. And in principle, we've provided a kind of relatively tractable method to study entropy inequalities, because again, it's no longer this question of I need to diagonalize these huge matrices or whatever. It's just a question of this algorithmic process of finding a map that satisfies particular constraints. So as our time is running out here, I just want to briefly mention some very interesting future directions for our work. So we have another result pertaining to the set of inequalities called the linear rank inequalities. Again, I won't go into too many details, but it's just some other set of entropy inequalities that are of interest in the quantum Shannon theory world, and we're able to find that there is a pleasant relationship between the hypergraph cone and these inequalities. But kind of one main direction of interest for us thus far has been we want to study whether this hypergraph entropy cone and the stabilizer entropy cone continue to coincide for higher party numbers. Now, shortly after we published, or sorry, not published, shortly after we put up the paper on the archive, Michael Walter and one of his students, Woodavine, they proved that stabilizer states realize all hypergraph entropy rays for all finite party number. That is, for all party numbers, the hypergraph entropy cone is contained within the stabilizer entropy cone. And they did this using like random tensor network technology, which is again a nice link between techniques developed for holography and quantum information. And so that's containment in one direction, and sort of some of the, where collaborators and I were currently working on proving the other direction. We're trying to think about how we can kind of build stabilizer states from hypergraphs, build hypergraphs from stabilizer states to prove that the hypergraph entropy cone contains the stabilizer entropy cone. And then kind of some other very clear directions are, obviously we're interested in higher party inequalities for the hypergraph entropy cone and getting in particular better bounds on the rank, so that again our bound, while it's nice that it exists, it's not very good for these very large inequalities, since there can be a lot of terms in these inequalities. And so ideally we'd like to get better bounds on the rank of hypergraphs that we consider for these entropies. And finally, our work suggests that there's really a more general connection between these kind of graph theoretic or network theoretic objects and quantum information or the structure of entanglement. So again, some kind of clear examples are bit threads. Min-cut exists for hypergraphs, and so there's some notion of flows on these hypergraphs, and so maybe there's some notion of bit threads that exists for hypergraphs that aren't holographic. There's other objects. Recently, collaborators and I, we were discussing this object called the Cheeger constant, which is important in graph theory, and so perhaps that has some application to understanding entanglement a little bit better. And I think I'm about out of time here, so we will call it at that. And yeah, thank you for listening to my talk.
Okay, so I think we can start our round of questions for Newton. And again, just a reminder, if you want to ask a question and you can turn on the video, that would generally help.
I actually have a question. This is Mark Willis speaking.
Mm-hmm.
Thanks for the nice talk, Newton. So you mentioned briefly that entropy inequalities are helpful for understanding energy conditions and gravity, and you said that among those participating in the call, that's well understood. I'm actually not familiar with that, so I was hoping you could just elaborate on that point a bit because it sounded very interesting.
Right. Well, we have Raphael Bousseau here, who is maybe the expert in this field. I don't know if you have a short tagline that you usually give, Raphael.
Yeah, I'm not 100% sure that I heard the question correctly, but I think it was about the relation between entropy and energy conditions in gravity.
Correct. Yeah.
And yeah, I mean, what we can say about that is that well, there are energy conditions which are important in many theorems in gravity, such as the area theorem and focusing theorem, which are known to be false, are known to be violated by various states in quantum field theory. And what appears to be the case is that we can obtain sort of quantum versions of these classical energy conditions that do hold, by, roughly speaking, by replacing wherever you see the area in the GR theorem, you replace it by the generalized entropy, which is the area plus the von Neumann entropy outside of a surface. And this works for surfaces which divide the world into two parts, basically. And so from that, for example, from that approach, which is basically just a guess about how quantum gravity should work or its semi-classical limit should work, various people, including myself and collaborators, have guessed semi-classical theorems in quantum gravity, which you can then check by taking a limit where you get a statement just about quantum field theory. And so those statements turned out to be non-trivial and actually provable from within quantum field theory. So an example of that is a condition on the stress tensor of matter, particular null component of the stress tensor being greater than a certain second derivative of the entropy with respect to a deformation of the shape of the surface that divides space into two parts. And so that's something that we now know is actually definitely true in relativistic quantum field theory, but it was actually discovered through gravity.
Thanks. I have a follow-up question related to what you were saying. So the discussion in the talk is about, from what I understood, entropy inequalities that hold for finite dimensional states.
Correct.
And to apply them in this context, do you need, does it suffice to have the entropy inequalities holding for separable Hilbert spaces, or do you need it in the von Neumann algebra context?
I am not sure about that. I don't think we've thought about these constructions in the infinite dimensional case at all. Yeah, I don't know. Ning, have you thought about them in the infinite dimensional case?
Sorry, my question was actually a follow-on to what Raphael was saying.
I see.
How these entropy inequalities have been useful in the context of quantum gravity.
I would say, so I think maybe we should leave this for the discussion and reserve the questions now for things that pertain directly to Newton's talk.
Sure, thanks.
Excuse me.
Can I ask what's known about the entropy cone for general states?
Yeah, so I think for general states, pretty much only the three-party entropy cone is known. So one of the obstacles has been that it's known that the full quantum entropy cone is not polyhedral. So you can't really describe it in these kind of nice extreme finitely many like extreme rays and facets, which just means that we don't have this nice geometric picture. You don't get this convexity, which is like really important because it means, again, we can describe the entire cone by this finite set of rays. So it doesn't have a lot of these nice properties. So yeah, not much is known besides those three inequalities I showed at the very beginning. You can make some conjectures, I think, but nothing is particular, at least to my knowledge, is particularly strong about like entropies of generic quantum states.
So one thing that you can think about in this context is trying to generalize yet further. So past hypergraphs. And we tried something that was a generalization past hypergraphs, but it turned out that the constraints that those give, I think, end up being the same as the hypergraph constraints. So it ended up not working. The short version of that story is that you can think of, you can convert any min-cut problem in a hypergraph, in an undirected hypergraph, into a min-cut problem on a directed normal graph with some infinite weight edges. And then the natural thing to consider is what happens if you take the infinite weight edges and you dial them down to finite weight. And so that will naturally give you some other set of states that, well, some other entropy vectors that you can look at. But long story short, in the end, it seems like the constraints on those, at least for low party number, are the same as those for hypergraphs.
Yeah. Oh yeah, and I did briefly want to mention that one of the, even at the stabilizer state level, which we kind of understand relatively well, we don't know what the 5-party stabilizer cone looks like, which is why this technique that we use doesn't work, because we don't have inequalities to work from. So we kind of have to use these direct construction methods to try to show containment instead of this nice, bounding inequalities and proving those inequalities are tight. We can't use that strategy.
Did you have any more questions for Newton? So if we do not, I would say let's thank Newton again. And
yeah, thank you for listening to the talk.